Hey guys, in today's video I will show how to create this lightweight particle system using Touchdesigner and GLSL node. Let's start from this simple scene, and first of all add the noise and make it achromatic, turn off monochrome, and add two nulls and call them position out and color out. For now we will set up our rendering system and instancing system, just to concentrate on the code on the second part of this video. Let's plug in noise onto both of the nulls for now, and let's add a subsphere and decrease its radius to something like 0.01, and then with middle click search for geo node. That's how it will be plugged in immediately, and turn on instancing on the instance tab. Drag position out onto translate operator slot and set XYZ to RGB set relatively, and on the color operator on the instance 2 tab drag color out node and use RGB to RGB conversion. We have some basic instancing now. Also let's add the floor, add a SOP grid, make it direction orientation ZX plane, and make it size 15 by 15. Also plug it into the geo node, and let's add the render top. And now we need a camera to render everything out. And here everything becomes laggy because I forgot to decrease amount of polygons on the sphere. On the detail tab, decrease rows and columns to 12 by 12. And now everything runs smoothly, at least on my PC. Then let's add a PBR material, assign it to both geos, and decrease metallic to something like 0.3 and roughness to 0.4. Let's add an environment light, and for environment map let's create another noise top and drag and drop it onto environment map slot and increase spheroids, decrease harmonics, and increase amplitude to make it more smooth, large scale, and contrast to kind of make a cheap HDRI map. And let's increase dimmer to 1.5 here. Also let's add the point light, set shadows to hard, and set shadow resolution to 4K by 4K to avoid some pixelated shadows. So our rendering system is set up. Let's go to the tabs. Let's add a GLSL node and constant top. Select constant GLSL and noise 1 tops, and in command tab choose 16-bit RGB, not RGBA but RGB, because we need only 3 values, X, Y, and Z for each one. Let's add constant chop to control resolution, add X and Y channels, set them to 128 each one, and again select Z tops and drag and drop to the resolution chop references of Z, X and Y channel of constant chop. And now we have control our resolution from one node. Let's disconnect that noise from our outputs. And next thing that we should do, we should set our constant to 0.1 and 0 color, kind of dark green, because it will be our starting position for all particles, and plug constant and noise tops into GLSL node. Then add a render select node and use a GLSL top as a reference inside of it, and duplicate it 2 times and set color buffer to 0, 1, and 2 for each node relatively. And into GLSL node, in GLSL tab, set number of color buffers to 3 to make it run correctly. And let's call it relatively position pass, velocity pass, and color pass. it will be our output, different 3 layers from GLSL node. Let's add feedbacks before our input in GLSL, and in first feedback, let's set our target top position path. In second feedback, let's set as input velocity path. And now we have 2 loops that goes through our GLSL node. To control that feedbacks, let's add keyboard in. Here I'm using keys Shift 1 and Shift 2 because they're not occupied by shortcuts of Touchdesigner. Select both feedbacks and drag and drop first channel to pulse button of that feedbacks. And now when I'm pressing Shift 1, feedbacks are pulsing and my simulation will be restarted. Now let's connect position path with position out, color path with color out, and press Ctrl E to open our fragment shader DAT into text editor. Now we should type in our outputs, first layout, location 0, out, vector 3 position out, duplicate it and make location number 2 for velocity out and location number 3 for color out. This is how we set up our render buffers that we will then execute from render select. And inside of the main function, let's sample position, texture, and velocity texture that we plugged into our GLSL node. Vector 3 position texture equals to sampling first texture and .rgb because we have only 3 dimensions and texture returns 4 dimensions. And then let's add a couple of variables, velocity new, and for now it equals velocity texture, and position new, it equals position texture. They will be used just for more easier way to manipulate them in future, and we should assign something to our output buffers. For now, position out will be position u and velocity out will be velocity new, so we just pass through parameters that we had on input. And for color out, I will use UVST and 1 to make just nice standard UV gradient. And now everything in 1 point because our position out is white, so everything in point 1, 1, 1, every particle. Now when we refresh our feedbacks, it will be that green coordinate, so a little bit above the floor. We need to add some movement to position, so every frame we need to slightly change our position, and let's add to our position new a little part of that velocity texture. So position new equals position texture plus velocity new multiplied by 001. And now we have some movement, but it goes only on one side because our noise is biased. First of all, I'm just fixing that alpha background. I'm setting it to gray to kind of be more like that grid on the ground. And then on the input noise, I'm setting offset to 0. Now everything goes in all directions, and set period to some small value, also to make our blast more uniform. The second problem is that our blast is going to all directions, but we need to be pointing upwards. So to this noise, I'm adding constant color with green channel active, and now our blast pointing upwards, but still has some diversity. And now we need to add some gravity because our particles should fall down somewhere, somehow. And let's add a g vector that will be equal to 0, -1, and 0, like in real life, it pointing downward. And let's change our velocity. Let's add for each frame to our velocity g multiplied by 0.03. And now, as you can see, particles start with up direction, but as time goes by, they're falling down because their acceleration become negative. So that's nice. Now we should add some bouncing. We could do it with if statement. We should detect if our position is lower than the floor. So if the position u dot y less than 0, then we should do something. And first idea is to invert our velocity y vector because it's pointing downwards, and when we're getting that collision, it should pointing upwards. So let's just type in velocity nu dot y equals minus velocity nu dot y. And it works somehow. We have some bouncing. It even looks nice. But some of the particles are falling through the ground. It happens because even if our particle is collided or above the ground, we still every time adding that g value and decreasing it for some small value, and even inversion doesn't work here properly. So let's fix that. First of all, we should change our position after all our conditions and velocity calculations, I suppose. And next thing, we should add some position prediction variable, because we just sometimes particle only will on this path falls through the ground but not falling right now, and we should take into account that position also. And only if position prediction is lower than 0, we should take our velocity texture, but in negative values, because our velocity texture variable is not affected by g for now. We're just using our previous acceleration. But as you can see, our spheres are kind of falling a little bit through the ground. They're showing on the different side because we're comparing it with 0 value. But our spheres has some radius, and it's radius of our sphere stops, 0, 0, 1 in this case. Let's add that and compare position post-predict.y with sphere radius, and plus 0 basically, but we don't need 0 in this case. As you can see, when I'm dead, everything now they're bouncing perfectly from the ground. Another problem that we have here is to bounce it. To decrease that bounce effect, we should multiply it by some smaller value, for example 0.7. And now they have 0 friction, and to make they stop for other axis, let's divide velocity nu xz by 1.2 just to slowly decrease the movement by x and z axis. So now we have nice bouncing. Let's add gravity control into vector stub onto GLSL. Let's add uniform gravity sign, add keyboard second channel from keyboard in onto first value, and let's declare it inside of our GLSL, uniform float gravity sign. That's how we can provide it inside of GLSL, and write down if statement after the g, that if gravity sign is equals 1, so if our k is pressed, then g dot y equals 1, it equals positive value, and gravity now pointing upwards. It works, but it works uniformly for all particles. It's kind of strange. That's why we need some random function. I will pick a random from the books of shaders site, but this random function is famous all over the net. Nobody knows where it's come from, but I will post the link to directly this page. And let's modify the gy value. Let's type in 0.6 plus 0.5 multiply by random with UV-ST coordinates inside of it. And that random function returns value from 0 to 1. That's why we have our new acceleration randomized. And also I'm adding a random to our default G, a little bit different value. I'm passing not UV-ST, but UV-ST plus .1, just to make some diversity from different randoms. everything is work just fine. Another little trick that we can do, we can multiply our color by power of our velocity. Length of velocity out will show how powerful velocity at the moment for each particle. And to be not completely black, we can add a 1 to this value and multiply it by 2. And now we have some nice dependence from velocity of particles to their color, and we can link multiple stuff with programming. That's nice. I'm adding here a constraint null to light and to camera, and in rotation y I'm typing in appstime.frame, and now I have rotation for camera and for light that kind of constant relative to the camera. Also, I will make some additional tweaks to the noise that used by HDRI to make everything look beautiful, and that's basically it. We did it. And another example of the flexibility of the system, I'm adding new uniform and provide it as attractor float value. And now if my Shift and 3 key pressed, everything attract to one center point that I declare as attractor chords in this code. And if attractor equals 1, so if my Shift and 3 key pressed, then I'm adding to velocity additional power. It consists of coefficient 0, 1 to just make it smaller, and inside of the normalize function, difference between attractor chords and position of each particle, and this difference shows the direction in which particle should move if we need to attract it to that point. And I'm using normalized to get uniform power for each of that vector, because they will be different if particle will be near or far, and normalize fix that, and every vector will be length of the one. That's why they attract similarly, and we can turn off normalize to have some nice effect also. That's basically it. Thanks for watching. I hope you enjoyed and learned something new. See you.